Okay, so Junior Roberts here with realjuniorroberts.com. We're doing a January 2015 CSEC Physics past paper, right? I'll be doing question 1 in this video, and in future videos I'll be doing or providing the solutions for the other questions in the paper. Now I'm actually putting together a complete package of past papers for you to actually help you prepare for your exams in January. So let's get right into this one. So it says here, a student carried out an experiment to investigate the temperature rise of 250 grams of a liquid when heated by an electrical immersion heater. The results of the experiment are recorded in table 1, and here we have table 1 with our results, right? And we can see we have 2 columns, one for the electrical energy measured in kilojoules and one for the temperature rise of water measured in Kelvin, right? And this is our values that were obtained in this experiment. Now the first part in this question, it says here we are to use the graph paper provided to plot a graph of electrical energy E against temperature rise delta T. Now as we know from before, whatever comes first in our statement we'll place it on our y-axis, and whatever comes last, which is in this case temperature rise, will go on the x-axis, right? So we're going to plot electrical energy on the y-axis and temperature change or temperature rise on the x-axis. And again, this is our table with our values, right? So we have our table here with our values, right, which is what we're going to use to plot our graph, right? And again, we're plotting electrical energy on our y-axis and temperature rise on the x-axis. So therefore our y-axis will go from 0 to 18 and the x-axis will go from 0 to 15. So let's look at our graph paper now. So this is our graph paper, right? I've started by ruling up the graph paper, right? So now we need to now actually select a scale, right? So looking back at our values, okay, so for the y-axis I'm using a scale of 2 centimeters to 2 units, and for the x-axis I'm also using a scale of 2 centimeters to 2 units. So let me go ahead and actually fill in these values, right? And that's my 2 axes with scale. Let me just actually indicate the scale that I use and what quantity will be on each axis. So for the y-axis I use a scale of 2 centimeter equal 2 joules, well actually it's kilojoules, right? And we're plotting energy E in units of kilojoules, right? While for the x-axis we use a scale of 2 centimeters equal to Kelvin, right? And on the y-axis we're plotting temperature change delta T, right, in Kelvin. Alright, so now that we have our 2 axes completely labeled, right, we can now start to plot our points. Alright, so let me just plot the points here. So the first point, right, corresponds to when the energy is 0, the temperature rise is also 0. So our first point will be just right here, right at the 0 mark, right at the 0 mark there, right? Then we have 3.7 corresponds to 3, right? So we have 3.7 on the y. So 3.7, right, this is 2 and this is 4, right? So therefore each of these is 0.2. So this is 3, 3.2, 4, 6, 8, well, 3.246. So 3.7 will be about right here, and that corresponds to 3. So that's right here. So we're going to place a marker there, right? And then we will continue. So we have now 7 corresponding to 6. So this here is 7 and corresponds to 6. So it's going to be right here. right there, right? And then 10.5 corresponds to 9, so we have 10 right here. 10.5 would be somewhere about this. 10.5 will be a little bit above here, so we can place it there, right, somewhere there, and it corresponds to 9 on the x-axis, right? And then we can continue. Then we have 14.5 corresponding to 12, so we find So we find 14.5 corresponding to 12. So this is 14 right here. So again, 14.5 will be slightly above. It's going to be somewhere like here. Right, and then we can continue. And we have 18 corresponding to 15. So find 18 right there, and corresponds to 15. So this is 14. So 15 is right here and corresponds right here. Right, so those are our points plotted. Right, now the next thing that we're going to do is actually now draw our line of best fit. So let's get out a straight edge to offer some guidance. Right, so we're going to line up our straight edge. Right, and to find the line of best fit in this case, it's relatively easy because the points are fairly nicely scattered. Right, as a matter of fact, there's not much scatter. Right, so our line of best fit should be quite a nice looking line. Right, so I'm trying to get the best line of best fit. Okay, so this looks to me as the best line of best fit. So it's kind of a bit redundant, but this is my line of best fit. So I have 1 point there, and it passes through these points. So right, I will go with this as my best fit line. So I'll draw my best fit line in this case. Right, so that's my best fit line. Right, now after we have drawn the graph, right, now also I need to actually put in my title, right, for the graph. So we're gonna say graph showing energy against temperature change or temperature rise. Right, and that's my graph, and I will underline with a ruler. Right, so that's my graph completed. Now the next thing that I want us to do now is to calculate the slope of the graph. And we know that the slope S is given by y2 minus y1 divided by x2 minus x1. Right, now what we need to do now is to select 2 points so we can actually get our y2, y1, x2 and x1 value. So let's go ahead and do that. Right, so I'm going to select 2 fairly reasonable points which will allow me to get my values fairly easily. Right, so I'm going to choose a point right here. So this is my first point. Right, and then this is I'm going to choose this point right here. Right, so I choose this point. So those are my 2 points that I have chosen, and as you notice the points are far apart. Right, so it allows me to get a much more accurate value for my gradient. So I'm going to read off the coordinates for y2, y1, x2 and x1. Right, so I will do that by using broken lines to indicate the values. So let me use this color here. So I'm going to make my broken line all the way down, right, like that, and I'll do the same for this one. Right, and then I will also do the same thing for the y-axis. Alright, so I'll go over to the y-axis, right, for both points so I can read off the corresponding values. Right, Now this point will give me my x2 and y2 values, while this point will give me my y1 and my x1 values, right? So if I read out from here, right, I'm seeing that in this case y2, right, is 19 because we have 18 right here and 20, and this is halfway, so it's going to be 19 here for y2, and y1 is just about 1.2, right? So we're going to fill in these values. Right, so y2 is 19 kilojoules, right, and y1 we said was 1.2 kilojoules, right, and we're dividing that now by x2 minus x1. So let's read out for x2 and our x1 values. So x2 in this case is 16, while x1 is 1, so we're going to just simply write 16 Kelvin minus 1 Kelvin, right? Now when we simplify this, 19 minus 1.2, that's simply 17.8 kilojoules divided by 16 minus 1 is 15 Kelvin, right? Now when we take the quotient of this, right, we have 17.8 divided by 15. Let's get out a calculator. So if we go, let's put the calculator here. So if we go 17.8 divided by 15, right, we get 1.186, right? So we can write this to 2 decimal place, right, or 3 significant figures, and we get it as 1.19, right? In this case it's going to be a kilojoule per Kelvin, right? Or we can simply write it as 1190 joule per Kelvin, right? Because remember this is kilojoules, so we just simply multiply this by 1000 and get 1190 joule per Kelvin as our answer, right, as the value for our gradient. Now if we continue the question, right, it says what physical quantity does the slope represent? Right, now there's 2 things we can use to find the answer for this. We can first of all look at what we plotted on our graph and also the answer we got for our gradient. So on our graph we plotted energy, right, against temperature change, right? We have energy against temperature change, right? So we have energy against temperature change, right? And also if we look at the answer we got for our gradient, we got joule per Kelvin, right? And the physical quantity that we know that have the unit joule per Kelvin is heat capacity, right? So therefore the physical quantity that is represented by our slope is heat capacity, right? Then now it says now use the value of the slope in 1b to determine the specific heat capacity of a liquid in units joule per gram per Kelvin. Assume there is negligible heat transfer to or from the container holding the liquid. So therefore to answer this question, right, we're going to consider the expression where we say that C, right, is equal to M times C, right? In this case this big C here is what is referred to as our heat capacity, right? M is our mass, right? And C is our specific heat capacity, right? So if we use this equation here, C is equal to MC, we are able to actually determine the value for our specific heat capacity. Right, so what we do is simply we transpose this formula here to make C the subject. When we do that, we're gonna have that C, which is our specific heat capacity, is equal to the heat capacity C, that is big C, divided by the mass. Right, now they said that we need to actually determine the specific heat capacity in units of joules per gram per Kelvin. Right, now earlier we would have already converted our heat capacity, right, from kilojoule per Kelvin to joule per Kelvin. So we are one step closer. So let's continue, right? And so therefore we're going to write our heat capacity as 1190 joule per Kelvin, right? And we're going to divide that by the mass, right? And since in our unit we have joule per gram per Kelvin, right, we have to ensure that the mass of the substance is in grams, right? So let's double check the value for the mass of the substance. So it says here that the mass of the liquid was 250 grams. So we can just simply plug that in our answer, in our equation here. So we have 250 grams, right? And then we take our calculator again. We're going to say 1190 divided by 250, right? And we get 4.76 joule per gram per Kelvin, right? And this would be our final answer. Right, now let's continue. Okay, so it says now the initial temperature of the water was 10 degrees below room temperature and the final temperature was 10 degrees above room temperature. How does this procedure help in minimizing errors in the experiment? Right, so we can see that basically what they did there was to ensure that they got a wide range of temperature values to minimize errors in the experiment, right? Because one of the ways in which we can minimize errors, especially random errors, is by taking multiple readings, right? So we can see that this is to ensure a large range of values are obtained to minimize random errors, right? So let's continue. So it says here now that given, well, first of all we need to, it says here to state one other useful precaution that the student should have taken, right? So since we're dealing with temperature change and we're going to use a thermometer to measure the temperature, right? We can say that ensure the thermometer is suspended in the liquid, right? Because you don't want the thermometer to be placed at the bottom of the container, right? If it is that you're using a beaker, you don't want the thermometer to be at the bottom of the beaker, because it will be actually measuring the temperature of the beaker, not the temperature of the water, and you don't want it to be too high in the water, so it is actually being exposed to the air and you're getting incorrect readings for the temperature. So now can continue, right? And it says here that given that the power supplied to the immersion heater was kept constant at 40 watt, calculate the time taken for 18 kilojoules of energy to be supplied. So for this, we're going to consider the equation where it says that power is equal to energy over time, right? So the power in watts is equal to the energy in joules divided by the time in seconds. Now in this case, I want us to find time, so we can simply transpose and make time our subject. Whenever we do that, we're going to get that t time is equal to energy divided by the power, right? So then now if we continue, right, we're going to get that time t is equal to the energy, which is 18 kilojoules. We're going to convert from kilojoules to joules by multiplying by 1000, so we're going to get 18,000 joules divided by, in this case our power is 40, so we're going to get 40 watt, right? And then we take our calculator for assistance and we say 18,000 divided by 40, right? And that gives us an answer of 450 seconds, right? Right, and that would be our final answer, right? And that would be the final part in this question. Now again, this is question 1. I'll be posting the solution for question 2 in another video. So again, this is Junior Roberts with realjuniorroberts.com. If there was anything in this video, please post it in the comments below and I'll do my best to clear up any misconceptions for you. Like this video if it was helpful and click subscribe and the bell notification so you're updated whenever I post new videos like this. Thank you for watching.